In this class, we want to be able to talk a bit about what capacitors get used for, and one of the topics we want to be able to discuss is how we can combine multiple capacitors together. Capacitors, like other circuit components, can be combined in one of two different ways, either in series or in parallel, and we have different equations that will govern how that works. To combine capacitors in series means that if you were to trace from the positive end of a battery through the capacitors to the negative end of the battery, you would have to go through a series of capacitors, first one, and then another, etc. Connecting several capacitors in series has the same effect as replacing them all with a single capacitor that has a lower capacitance. So adding them makes them less effective at storing charge. In this case, the equation is at the bottom of the screen. 1 over the series capacitance total, that's what the C subscript S stands for, is capacitance series, equals 1 over capacitance 1 plus 1 over capacitance 2 plus 1 over capacitance 3. To combine capacitors in parallel means that if you were to trace from the positive end of the battery through the capacitors to the negative end of the battery, you have multiple paths available to you, but you don't encounter every capacitor along any given path. Connecting several capacitors in parallel has the same effect as replacing all of them with a single capacitor that has a greater capacitance. Adding them together makes them more effective at storing charge. In this case, the equation is that the total capacitance in parallel, C subscript P, equals capacitance 1 plus capacitance 2 plus capacitance 3. Really straightforward. Of course, it's easy for me to say that these equations are easy and straightforward. I'm sure that you would feel better if we went through a couple of examples, so let's do that. In this first one, it says to determine the total capacitance if 3 capacitors are connected to a 1.5 volt battery in parallel with each other, given that each capacitor is 300 microfarads. What charge will that array of 3 capacitors in parallel hold? Well, they're in parallel, so I really do just get to add them together. 300 microfarads plus 300 microfarads plus 300 microfarads equals 900 microfarads. That's their total capacitance. And to find the charge that they hold together, I go to the equation Q equals CV, and I take the total capacitance and multiply it by the 1.5 volt battery, and I get that the total charge that the 3 of them combined will hold is 1,350 microcoulombs, or 1.35 times 10 to the minus third coulombs, millicoulombs. So that really was easy. Let's try another example and see if it continues to be that easy. Determine the total capacitance if 3 capacitors are connected to a 1.5 volt battery in series with each other, given that each capacitor is again 300 microfarads, and then find out what charge it will hold. Well, the equation that we have is 1 over the total capacitance equals 1 over C1 plus 1 over C2 plus 1 over C3. There's a couple ways you could do this. One is to algebraically solve for C total first. The other one is to just say I'm going to plug numbers in for C1, C2, and C3, the capacitance of my 3 capacitors. They won't always be equal to each other, but in this case they are. So I can say 1 over the total capacitance is equal to 1 over 300 times 10 to the minus 6th farads plus 1 over 300 times 10 to the minus 6th farads plus 1 over 300 times 10 to the minus 6 farads. And I could just put that into the calculator. 1 over 300 times 10 to the minus 6th plus 1 over 300 times 10 to the minus 6th plus 1 over 300 times 10 to the minus 6th. And I get 10,000 as the value. But that's 1 over the total capacitance is 10,000, and the units for that are 1 over farads. So I need to solve that for C total, which is in the denominator on the left side of this equation. So you want to make sure that by the time you are over here at capacitance total, you've pulled your variable out of the denominator. The total capacitance should be 0.0001 farads. And then to find the charge on that, you again put it back into Q equals CV, where V is the voltage from the battery being applied to this array of capacitors. And I get that that comes out to 1.5 times 10 to the minus 4th coulombs. Still not too difficult as long as you don't rush through and allow yourself to get tripped up by the algebra. Realistically, in a problem, you're not likely to have all the capacitors be the same as one another. So you might have something like a 40 microfarad capacitor is in series with a 775 nanofarad capacitor in a circuit that has 4.4 volts across it, and you are asked to find the total capacitance and the charge stored. So what you want to do first is make sure that you're very careful about whether these are in series or parallel. These are in series, so I can't just add them together. I need to find the equation 1 over the total capacitance in series equals 1 over C1 plus 1 over C2. The next step is that I want to be very careful with my math, including the fact that a micro is not the same as a nano. I want to make sure that I'm putting in the correct metric prefixes. So if I do that carefully, I would then wind up finding out that the total capacitance is 7.6 times 10 to the minus 7th farads. Please do check that you get the same thing when you walk through the mathematics. And if you're not getting the same thing, see if you can figure out why. It's always possible I've made an error, but I think in this case I didn't. The amount of charge on the array is, of course, again, Q equals CV. So I take the total capacitance that I just calculated and I multiply that by the voltage that was provided in this question. It was 4.4 volts. And I get that the total charge is 33.44 times 10 to the minus 7th coulombs. So we can mix things up a little bit, but it still is pretty straightforward if you'll take your time with the math. Now, it is definitely possible that we could make this more complicated by having, for example, a circuit that has some combination of series and parallel. And each parallel branch in this case would have to be added together first as a series of 2 capacitors in the left branch and then a series of 2 capacitors in the right branch. And then we would combine these 2 parallel branches using the equation for parallel branches. This could get really complicated, and it should if you are studying electronics. But if you are in an intro course, we just want to make sure that we know what the tools are, and we don't need to press on this for the next couple of weeks or something like that. So the way this might look is something like this. My 4 capacitors are labeled, and it's asking me what is the total capacitance if capacitor 1 is 14 microfarads, capacitor 2 is 50 microfarads, capacitor 3 is 112 microfarads, and capacitor 4 is 87 microfarads. Again, the first thing I want to do is recognize that the total capacitance is going to be the left branch plus the right branch because they are in parallel with one another, but I can't take those values and add them together yet because I don't know what the total capacitance in the left branch is, and I don't know what the total capacitance in the right branch is. So I would say 1 over the total capacitance in the left branch is equal to 1 over capacitor 1 plus 1 over capacitor 2. And I put those numbers in carefully, and I determined that the capacitance in the left branch is 10.9 microfarads. I then do the same thing on the right side, saying 1 over the capacitance in the right branch is equal to 1 over capacitance 3 plus 1 over capacitance 4. And again, if I'm careful with my math, I get that the capacitance in the right branch is 49.0 microfarads. Then I can just add those 2 branches together using the equation for parallel capacitors, because what we've effectively said is I can replace these 2 capacitors with one capacitor that has a capacitance of 10.9 microfarads. And I could replace these 2 with one capacitor that has a capacitance of 49 microfarads. Adding together 2 capacitors in parallel with each other, 10.9 microfarads and 49.0 microfarads, I just add them together, and I get the total capacitance of this entire circuit is 60 microfarads. I think in class I'd like to throw another example at you and see if you can figure out how to break it apart into pieces and determine the total capacitance, but that's not really our focus for the course. So again, we'll make sure that we know the basics of how to do it and then now recognize that there's a limit to how far we want to take that.